Assalamualaikum. Today our group represent the application of the solving differential equation with eigenvalues.
So moving on to introduction, what is hyperbolic structure? Hyperbolic structure is known for their strength, which is their curved surfaces resembling saddles, and also its elegance. So the motivation behind this is to unravel and to explore complexities as well as emphasis analytical tools. So what is mathematical tools in action? So the advantage of using hyperbolic structure is easy large spans and also the minimal materials to do it. And also the challenges behind this is the behavior analysis, and it demands precision of understanding the behavior under various loads. So the hyperbolic structures in the real world is an application in the Seattle Space Needle, where it is a nuclear power plant, as you can see here. So why do we do this presentation is to deepen the understanding and also contributing insights about hyperbolic structure.
Next, we are going to discuss on the methodology of solving differential equation in eigenvalue problems. First, mathematics is a fundamental tool in various disciplines, and linear algebra plays a crucial role. Eigenvectors and eigenvalues are key concepts in linear algebra, and we can see the application of eigenvectors and eigenvalue in computer science, physics, and engineering. Next, one of the application of eigenvectors and eigenvalues is in the hyperboloid 3D shapes. A hyperboloid is a quadratic surface which a generalization of conic section consists of ellipses, parabolas, and hyperbolas. So there are two types of hyperboloid shapes, which are hyperboloid one sheet and hyperboloid two sheets. Hyperboloid of one sheet is possibly the most complicated of all quadratic surfaces because of its confusing equation, and because of its cross sections are quite complex. So we can see the general equation of the hyperboloid equation in the slide. So for the hyperboloid equation of one sheet, it is equal of positive 1, and for the hyperboloid of two sheets, it is equal of negative 1. And for the generalized equation of hyperboloid, we can see the equation in the slide, where x minus v transpose and a x minus v is equal to 1. And according to Hilbert, the one sheet hyperboloid has two positive eigenvalues and one negative eigenvalue, while the two sheet hyperboloid have one positive eigenvalues and two negative eigenvalues. And the eigenvector of A is defined the pre-simple direction of hyperboloid, and the eigenvalues of A are the reciprocal or multiplicative inverse of the squares of the semi-axis, with the equation of 1 over A square, 1 over B square, and 1 over C square. Overall, eigenvalue problems are a powerful tools in the analysis and design of hyperboloid structures. We can see the application of eigenvalue problem in hyperboloid shapes in various structures and in cooling towers, where the shape facilitate efficient air circulation and heat dissipation, and making it essential component in thermal power plants and industrial processes.
Next, take the example. Perform a rotation of axis to eliminate the xy term in the quadratic equation like in this picture. First, we need to find matrix A from the equation, and you need to find the eigenvalue using the formula. And then you will solve it, and you will get the eigenvalue equal to 8 and negative 2. After we get the eigenvalue, we need to find the eigenvector using the formula A minus lambda I. And you will use Gaussian elimination to find the eigenvector. So the eigenvector for eigenvalue 8 is equal to negative 1 and 1. Next, we use the second eigenvalue, which is -2, to find the eigenvector using the Gaussian elimination. And you will get the eigenvector is 1, 1. And after we get these eigenvectors, which is -1, 1, and 1, and 1, you will need to normalize these eigenvectors to find the columns of P. And then you need to find the determinant P, which is equal to 1. And you need to form this matrix to P cosine, negative sine, sine, and cos theta. And from here, we get the angle, which is 135 degree, to tell it the rotation of the equation. Next, you need to find the matrix product of DE Px prime, and you can substitute this formula using the from the equation, and lastly you will get negative 16x prime plus 16y prime. So we can combine this equation based on the rotated cone equation, and lastly you will get like this. So from the equation, we can see that the equation will turns to hyperbola graph.
Now for discussion, the aim is to investigate the mathematical framework for such conic rotations related to hyperbola by solving the relevant differential equation with eigenvalues. For the contents of the discussion, we have two main points, which are why eigenvalues can find hyperbola graph and how differential equation related to hyperbola. Why eigenvalues can find hyperbola graph. Eigenvalues are essential for finding the graph of a hyperbola to the rotation of a conic hyperboloid because they indicate how much and in which direction the conic section is rotated in the new coordinate system. These eigenvalues simplify the mathematical equation involved, making it easier to express the hyperbola's orientation and scale. In essence, eigenvalues guide the transformation, helping us understand and graphically represent the resulting hyperbolic shape after rotation. Based on the question before, eigenvalues play its role to find eigenvectors that are responsible to get the trigonometric values that can plot to the graph. The shape of hyperbola managed to be plotted. How differential equation related to hyperbola. A hyperbola differential equation describes the mathematical behavior that governs its shape and orientation. The mathematical representation of the hyperbola is revealed by solving the differential equation, and certain elements of the solution, such as eigenvalues, determine the hyperbola's characteristics, such as rotation and scaling. The differential equation is a mathematical tool that can be used to represent and understand the dynamics of a hyperbolic curve. Based on the query and the specific differential equation of the question before, a hyperbola graph can be produced by obtaining eigenvalues and eigenvectors and connecting them with a rotated conic equation.
So in conclusion, the future of hyperbolic structures, where we can envision and imagine the earthquake-resistant skyscrapers swaying gracefully with the design influenced by intricate dance of differential equation and also the eigenvalue problems. And we can see bridges dancing in the wind in the form of hyperbolic structures resonating in harmony with the wind itself. So the mathematical symphonies of differential equation and eigenvalue problems redefine possibilities in a world full of innovation.